It is really funny how quickly we just get used to magic.
Oh, completely. We take it entirely for granted.
Right. Like every single day, you probably dictate a text message to your phone while you're just walking down the street. Or you type half a question into a search engine, and it just instantly finishes your sentence for you.
Exactly. It knows what you want before you do.
Yeah. You interact with it constantly, but you probably rarely stop to think about the massive invisible machinery making all of that happen. So welcome to the Deep Dive. Today, our mission is to decode that exact machinery.
It is quite the rabbit hole.
It really is. We are looking at a comprehensive overview of natural language processing, or NLP, to figure out exactly how computers learn to understand, process, and even generate human language.
And the journey to get to this point is just full of surprises, dead ends, and some truly profound questions about what it actually means to communicate.
Oh, absolutely.
We're going to see how the scientific community had to, completely change its mind several times over the decades to finally crack this code.
It is a wild ride. And to get our heads around the core challenge here, I want you to imagine trying to teach a highly logical, incredibly literal-minded alien how to appreciate a poem.
That is a great analogy.
Because for a computer, the math part is easy, right? Crunching numbers, storing massive spreadsheets, no problem at all. But human language is a nightmare.
It really is.
It's messy, it's full of sarcasm and double meanings, and the rules are broken as often as they are followed.
If we connect this to the bigger picture, it is crucial to understand that NLP isn't just about building a better spell check. In the field of computer science, mastering natural language is actually considered an AI-complete problem.
Wait, AI-complete? That sounds intense.
Yeah, it does. What it means is that to fully solve language, to get a machine to truly comprehend it the way you or I do, you essentially have to solve artificial intelligence itself.
Because language doesn't exist in a vacuum.
Exactly. To understand a sentence, you need real-world knowledge. You need an understanding of context, and you need logical reasoning. You can't just program a dictionary into a machine. You literally have to program an understanding of the entire human experience.
Which is exactly why the early attempts to solve this problem were just, so overly optimistic.
Oh, they were incredibly naive.
Right. To understand how we got to the seemingly magical AI you have in your pocket today, we really have to start with how early computer scientists in the 1950s thought language worked. Basically, they treated it like rigid algebra.
Yeah, the roots of NLP go all the way back to Alan Turing in the 1950s. I mean, he proposed the Turing test, which inherently relied on a machine's ability to interpret and generate natural language to prove its intelligence.
Right, the ultimate benchmark.
But the real burst of early confidence, though, that came in 1954 was something called the Georgetown experiment.
Oh, the Georgetown experiment, where the researchers managed to get a computer to automatically translate over 60 Russian sentences into English.
Exactly. And based on that tiny, highly controlled success, the authors boldly claimed that machine translation would be a completely solved problem within, 3 to 5 years.
Wow. 3 to 5 years to solve language.
It's a classic case of underestimating the complexity of a problem. They thought language was just a matter of swapping words and applying a few structural rules. Like, you look up the Russian word, you find the English equivalent, you swap them, and you apply a grammar rule.
Boom, done.
Right. But real progress was agonizingly slow because language isn't just a simple cipher. And by 1966, a famous evaluation called the ALPAC report came out.
Oh, yeah, the ALPAC report. That was devastating.
It brutally concluded that 10 years of really expensive research had basically failed to fulfill any of those grand expectations.
And that report didn't just hurt feelings. It crushed the entire industry. Funding for machine translation in the U.S. was dramatically slashed, and serious research was largely paused until the late 1980s.
Yeah, that whole era is often referred to as symbolic NLP. The philosophy was basically to hand code complex sets of rules to manipulate symbols.
Which sounds good on paper.
Sure, but to understand the fundamental flaw in this approach, you just have to look at John Searle's famous Chinese room thought experiment from the source text.
Okay, lay that out for us.
So imagine a person locked in a room who doesn't speak a single word of Chinese. They are given a batch of Chinese writing and a giant rule book in English. And that rule book tells them exactly how to match certain Chinese symbols with other Chinese symbols to form answers.
So to the people outside the room slipping questions under the door, it looks like the person inside is perfectly fluent in Chinese.
Exactly. They are getting totally coherent answers back, but the computer or the person in the room is just emulating understanding by blindly applying rules to the data it confronts.
There's no actual comprehension happening.
None at all. The machine is just moving shapes around a board.
But they did have some wild successes in the 1960s, even with severely limited computer memory. I mean, there's a program called SHRDLU, which could understand commands about manipulating toy blocks in a restricted vocabulary.
Yeah, SHRDLU is a big deal.
And then there was ELIZA, created by Joseph Weizenbaum between 1964 and 1966, and that simulated a psychotherapist.
ELIZA is such a fascinating milestone because it highlights the human side of the equation.
Okay, let's unpack this. If ELIZA was just following these rigid mathematical rules without any real comprehension, why did people feel so deeply connected to it? Like, users reportedly shared incredibly intimate personal details with this program, treating it like a real living therapist.
Well, because ELIZA was a brilliantly designed illusion. It used almost no information about actual human thought or emotion. Weizenbaum designed it so that when the patient, the user, exceeded the program's very small knowledge base, the system would simply fall back on generic deflections.
Oh, I see.
Yeah, if you typed, "My head hurts," ELIZA would just turn it around and say, "Why do you say your head hurts?"
Oh, wow. It mimicked the active listening of a therapist.
Precisely. It didn't need to understand pain, it just needed to reflect the statement back as a question. This made humans project empathy onto the machine.
That's incredible.
But underneath it all, rule-based systems hit a massive wall.
Because language is just too weird. You can hand-code rules for the most common sentence structures, sure, but human language has an infinite number of rare, weird exceptions.
Absolutely.
You simply cannot manually write an algebraic rule for every single edge case. The complexity becomes totally intractable.
Which is why the scientific community had to completely pivot. Because human language had too many exceptions for handwritten rules, scientists in the late 1980s and 1990s realized they needed a completely different approach. They stopped trying to teach computers grammar, and they started teaching them probability.
Here's where it gets really interesting. This is the statistical revolution, and it officially ended that long AI winter where funding had totally dried up.
Yeah, finally.
Instead of linguists writing out complex syntax trees by hand, computer scientists started using machine learning algorithms.
And two crucial things fueled this shift. First, Moore's law meant computers were finally getting the processing power and memory they needed to handle massive amounts of text.
Right.
But second, there is a huge philosophical shift away from the dominant linguistic theories of the time, particularly those championed by Noam Chomsky.
Ah, Chomsky. He argued for something called the poverty of the stimulus.
Exactly.
The basic idea was that human children don't get enough exposure to language data to learn all its complex rules from scratch, so the foundation of language must be hardwired into our brains.
Yeah, that was the prevailing thought.
And because of that theoretical underpinning, scientists were actually discouraged from using real-world corpus data, which is just massive collections of text, because the theory essentially said general learning algorithms wouldn't work on language.
But the computer scientists decided to try the data anyway.
And it worked beautifully.
It really did. IBM Research had a massive breakthrough in machine translation by feeding their algorithms existing multilingual texts. And the texts they used are so perfectly mundane. It was the translated proceedings of the Parliament of Canada and the European Union.
Which is so clever when you think about it. Because the law required those governmental proceedings to be translated into all official languages, it created a perfect, naturally occurring data set.
Yes. The algorithm could look at a sentence in English, look at the exact same sentence translated into French, and statistically calculate the probability that a specific word translates to another specific word.
Then the 2000s hit, the World Wide Web exploded, and suddenly we had endless, raw, unannotated data.
Oh, it was a goldmine. We moved right into unsupervised and semi-supervised learning. The machine could just absorb millions of web pages and learn the statistical likelihood of which words follow other words.
To put this in perspective for you, symbolic NLP, that 1950s approach we talked about, is like trying to navigate a new city using only a rigid paper map and a dictionary. You are constantly stopping to look up rules, and if a street is closed, you are completely lost.
You're stuck.
Right. But statistical NLP is like learning a language by moving to the country, binge-watching foreign TV shows, and absorbing the patterns until it just sounds right.
What's fascinating here is that these statistical language models turned out to be far more robust than the old rule-based systems. I mean, a rule-based system breaks if you misspell a single word because the rigid rule just no longer applies.
It crashes.
Exactly. But a probabilistic model, it has seen that exact misspelling 1,000 times in its web data. It calculates that there is a 99% chance you meant to type hello instead of hello.
It knows what you probably meant.
Yeah. With the statistical approach, the larger your probabilistic model becomes, the more accurate it gets.
Counting words and calculating probabilities was a huge leap, but those statistical methods still required a lot of human hand-holding. Engineers had to do elaborate feature engineering, which basically means they had to manually tell the system what linguistic features to look for.
Right, like pay attention to verbs here, pay attention to adjectives there.
Exactly. But the next evolution, starting in the 2010s, removed that human hand-holding entirely.
Yeah, the transition really started gaining ground when neural networks began outperforming the best statistical algorithms. In 2003, a multi-layer perceptron neural network beat out older models. Then in 2010, a researcher named Tomasz Mikolov applied a recurrent neural network to language modeling.
And that eventually led to a breakthrough tool called Word2Vec.
Yes, Word2Vec.
We hear the phrase neural networks all the time, but the way they tackle language is just wild. We entered the era of deep learning and representation learning. The machine was no longer just counting how often two words appear next to each other, it was figuring out the hidden representations and relationships between them.
Word2Vec is a perfect example of this. Instead of just seeing words as isolated text, it turns words into multidimensional mathematical vectors. It maps them in a vast mathematical space.
Okay, how does that work?
So the distance between the vector for king and queen becomes mathematically similar to the distance between man and woman. The network discovers these underlying semantic relationships purely on its own, without a human ever defining what gender or royalty even is.
Wow, it made all those intermediate manual steps, like manually aligning words, totally obsolete.
Completely.
But wait, before the neural network can map all these concepts, it still has to break the raw text down into pieces it can actually ingest. You can't just swallow a whole book at once.
No, it can't. That process is called tokenization. It means dividing text into fragments tokens and giving them numerical identifiers. For a machine to process a sentence, it has to turn the words into numbers.
Wait, for English, isn't tokenization ridiculously easy? You just look for the blank spaces between the words.
Well, yeah, it is easy for English, but think about languages like Chinese, Japanese, or Thai.
Oh, right. They do not mark word boundaries with spaces. A sentence is just a continuous string of characters. To segment text in those languages, the system needs a deep, complex knowledge of the vocabulary and the morphology of the language. You can't just look for a blank space. The algorithm has to mathematically deduce where one word concept ends and another begins based on surrounding context.
And it has to be even harder when we move from perfectly typed text to just talking to our phones. When I speak to my voice assistant, I am definitely not leaving neat little spaces between my words.
Speech recognition is incredibly difficult because of a phenomenon called co-articulation.
Co-articulation.
Yeah. When humans speak naturally, the sounds representing successive letters actually blend together. The end of one word slurs right into the beginning of the next. Your human brain separates them effortlessly based on context. But converting that continuous, unbroken analog sound wave into discrete textual characters is a massive hurdle for a machine.
That makes total sense. Add in the wide variety of human accents, regional dialects, and just random background noise, and it's a monumental computational task.
But the payoff for cracking this is huge. You pointed out in our notes how these neural approaches are revolutionizing healthcare right now.
Oh, absolutely. NLP is unlocking unstructured text in electronic health records. Doctors write notes in shorthand, full of obscure jargon, messy syntax, and acronyms.
Right. Chicken scratch, basically.
Yeah, and traditional databases can't read that. But neural NLP can read those unstructured notes, analyze them to spot early warning signs for patient care, and simultaneously strip out sensitive terms to protect patient privacy. It's turning locked away, messy text into actionable medical insights.
So we've got the computer perfectly transcribing our blended speech, and it has successfully tokenized the words into numbers. But identifying a word is very different from actually understanding what it means in the real world.
Extremely different.
This is where we hit the absolute wildest quirks of human communication.
Meaning is incredibly messy. Let's start with just figuring out the base form of a word. When a machine sees words like running, ran, and runs, it needs to know they all stem from the same concept.
Right.
You have two approaches for this: stemming and lemmatization. Stemming is the older, rougher method. It operates like a butcher knife, just chopping the ends off words based on rigid rules, so closing becomes close. Sometimes it chops off so much you are left with a non-word.
Which isn't ideal.
Not at all. Lemmatization is much smarter. It acts more like a librarian. It actually references a comprehensive dictionary to analyze the word's morphology and return the true base word, which is called the lemma. It knows that the lemma of better is good.
Oh, wow. Then you have word sense disambiguation, or WSD.
Yeah.
This is the classic problem of words having multiple meanings. If I say book a flight versus read a book, the machine has to look at the surrounding context to know if book is functioning as an action verb or a physical noun.
Exactly. And that leads directly into named entity recognition, or NER. This is how a system figures out if a word is a proper name, a location, or an organization. You might think the machine could just look for the capital letters.
Which works great in English, but not globally.
Right. In German, every single noun is capitalized, whether it's a specific person's name or just the word for apple. Arabic doesn't use capitalization at all, and in Spanish and French, they don't capitalize names when they are serving as adjectives.
Wow, I didn't even think of that.
Yeah, so the machine cannot rely on punctuation. It has to infer the entity entirely from the complex mathematical context surrounding it.
And then there's discourse and conference resolution. The source text gives this great example. He entered John's house through the front door. The system has to know that the front door specifically acts as a bridge to John's house, not just some random door down the street.
Exactly.
So what does this all mean? Coreference resolution sounds exactly like trying to keep track of all the characters and their varying nicknames in a dense, 1,000-page Russian novel.
That is a perfect way to describe it. Humans use these bridging relationships effortlessly. We know the front door belongs to the house that was just mentioned. But for a machine, every single pronoun, every he, she, it, or thee is a puzzle piece.
It's just a blank.
Yeah. It has to be mathematically resolved against the local text. It's an intricate web of dependencies. And once you resolve all those entities and pronouns, you can do incredibly useful things like sentiment analysis.
That's where you categorize the emotional tone of text as positive, negative, or neutral. It is exactly what companies use to automatically analyze millions of customer reviews to see if people actually like your new product or hate it.
Right. But understanding all that context is just half the battle. Once you crack the code of meaning and context, the machine doesn't just sit there processing language quietly. You start generating it at scale.
And the evolution of text generation is just fascinating to look at. Back in 1984, a rule-based system named Ractor generated an entire book called The Policeman's Beard is Half Constructed.
Catchy title.
Right. But it was entirely nonsensical, just stringing words together based on those rigid grammar rules we talked about earlier.
Decades later, in 2018, a neural network generated a novel called Won the Road, which was 60 million words long. But again, it was basically semantics-free. It sounded vaguely like a road trip novel, but it meant nothing. It lacked a coherent narrative arc.
But by 2019, things shifted dramatically. A machine generated a science book called Lithium-Ion Batteries, published by Springer.
Oh, that was a huge milestone.
Yeah. Unlike the previous examples, this wasn't hallucinated nonsense. It was grounded in actual factual text summarization. The machine read vast amounts of chemistry research and synthesized it into a coherent, structured book.
We are moving past just parsing sentences into something that looks a lot like cognition. We are trying to emulate intelligent comprehension. The source dives into George Lakoff's theory of conceptual metaphor, which argues that to truly master language, a computer must understand intent.
For instance, if I say, that is a big tree, I am clearly talking about physical size.
Right.
But if I say, tomorrow's a big day, I am talking about importance. But wait, I have to challenge this. If a computer doesn't actually have a physical body, it doesn't experience time, and it has never felt anxiety about an upcoming event, how can it ever truly understand the importance of a big day? It's just lines of code.
This raises an important question, and the answer lies entirely in mathematics. The algorithm doesn't feel anxiety or importance. Instead, the source text outlines a formula for this called the relative measure of meaning, or RMM. It calculates the intent mathematically by looking at the mathematical neighborhood of the words.
Okay, how does that mathematical neighborhood actually work?
It takes the probable measure of meaning based on the massive data sets it was trained on and multiplies it by a probability function that scans the specific tokens located immediately before and after the phrase being analyzed. So if big is next to day, the algorithm scans the wider sentence and might see words like wedding, graduation, or nervous. It calculates that in this specific mathematical neighborhood, the word big lives much closer to the concept of important event rather than physically giant 24 hours.
Wow.
Yeah. By assigning these relative measures of meaning, the algorithm uses complex probability to mathematically approximate human cognitive intuition.
It's just staggering to think about. We've gone from the naive optimism of those 1950 scientists handwriting rigid algebra rules and getting crushed by the LLPAC report to feeding mundane Canadian Parliament records into early statistical models,
Quite the leap.
and all the way to massive deep neural networks that turn words into multidimensional vectors just to calculate the mathematical weight of a human metaphor.
It's a testament to the sheer power of massive data, computational scaling, and, the willingness of the scientific community to abandon their old assumptions when they hit a wall.
I really want to thank you for joining us on this deep dive into the source material. We interact with this invisible machinery constantly, and I hope the next time your smartphone automatically filters out a spam email or correctly guesses the end of your text message, you have a newfound appreciation for the decades of complex mathematics making it happen.
It is incredible. But as we close, I want to leave you with one final thing to ponder.
Ooh, lay it on us.
We've seen how computers have completely abandoned human-made grammatical rules. They aren't learning syntax trees. They are now mastering language purely through statistical patterns hidden in massive, uninterpretable neural networks. So when that machine accurately summarizes a medical record or writes a coherent science book, does it actually understand us? Or have we simply built a perfect mathematical mirror, one that brilliantly reflects our own thoughts back at us without a single drop of real comprehension?